When a particle repeats the same motion over and over again, that's periodic. However, if it moves the same way that a mass on a spring would move, that's simple harmonic motion. If you imagine putting a mass on a frictionless table, attach it to a spring that's connected to the wall, and let it slide back and forth, it will be moving in simple harmonic motion. If you put a pin on this mass and pulled a piece of paper up from the floor to the ceiling near the pin, you'd see it trace out a sine curve like in this animation below. We can connect the frequency with that motion. The number of complete periods that it makes, or complete oscillations it makes in 1 second, is the frequency, and the period is the time it takes to make one complete oscillation. So frequency would be measured in inverse seconds, which are also called hertz. And we can also define an angular frequency, which is 2 pi multiplied by this frequency in hertz. That would be radians per second again. This, we'll see why later we might want to attach an angular frequency to this. But the thing that generates simple harmonic motion is if you have a restoring force, which is what brings it back to equilibrium, the system. If that's proportional to the displacement, that's how you end up with simple harmonic motion. For a mass on a spring, the restoring force from the spring is negative k times the displacement, which we usually write as negative kx. If that's the only force on the mass, Newton's second law gives us negative kx equals max. And this looks very simple, but if you remember air resistance was the same way, this is a differential equation, not an algebraic equation. Ax is really a function of x. Now, you don't have to be able to solve differential equations because you haven't had that class yet, but you should be able to verify whether something is a solution or not, because that just requires calculus. If I tell you that x as a function of time is a times the sine of omega t, or we could use cosine of omega t, you can verify that that's a solution by plugging it in to the left side and right side of this equation. And you see that what you get is this will work as long as omega is the square root of k over m, the spring constant over the mass. This constant a is the amplitude. That's the furthest away the spring gets from equilibrium, its most extreme extension or compression. Sometimes instead of a, this is written as x sub m or x max. And there's one more constant that we would put in this for a general solution. The first day of class, when we looked at objects that were falling under the acceleration of gravity, for most of those problems we had a equals negative 9.8 meters per second squared, but there was still a lot left to solve in that problem. You also need to find other things, and typically that might be x and v initial values. This equation that we have here, a simple harmonic motion, that's also a second order differential equation. So again, we need to know position and velocity at some particular instant of time if we want to pick this out. The way we describe this is something called the phase constant, phi, and this fits into the solution like this. We change it to a sine omega t plus phi, or a cosine omega t plus phi. And of course the phi would be different in each case, because sine and cosine are different by 90 degrees. Really, there's no difference. If someone drew a sinusoidal curve on the board, but there was no axis there for you to see what value it had at what particular time, you couldn't determine whether it was a sine or a cosine. So phase is the only thing that separates them. If we know x is a function of time, we can find velocity as a function of time very quickly just by taking the derivative. If we use a sine omega t plus phi, we get that the velocity as a function of time is a omega cosine omega t plus phi. If we had written it the other way, we would get velocity is negative a omega sine omega t plus phi. The way we determine the value for phi is by looking at the initial conditions. So if we have a mass on a spring, and at t equals 0 it's at the origin and is moving to the right, positive x, we know that x0 equals 0 and v0 equals positive v max. It's at its fastest because all the energy is kinetic at that point. And v max will be omega a. I can see that by looking at this form for v as a function of t and realizing that cosine will never be larger than 1. So that tells me the maximum value of velocity must be, when cosine is 1, so V is omega A. If we use sine for our solution, x of t is a sine omega t plus phi, we can solve this and find the constant. We know that x at t equals 0 is 0. We plug in 0 for time. So we need the sine of phi to be 0. There are two solutions for this. We could use phi equals 0 or phi equals 180 degrees. We can't pick which one just by looking at x. We have to look at v also. If we use x is a sine omega t, we get v is omega a cosine omega t. If we plug in a t equals 0 for that, that tells us v at 0 is cosine of phi times a omega. V at 0 has to be a omega, so the only solution that works is phi equals 0. If we try and put in phi equals pi, or 180 here, we'll get that the velocity at time 0 is negative omega a. What would we get if we used the cosine solution instead? Again, we know that at t equals 0, x has to equal 0, so we plug it in. Now we want a phi that will give us 0 if we take the cosine. So our choices are 90 degrees or 270 degrees. And again, we look at v to figure out which one we want. V is then going to be negative a omega sine omega t. We plug in 0 for time. V is negative a omega sine phi in that case. And since we know v at 0 has to be positive omega a, the only way this works is if phi equals 270 degrees. For another example, if at t equals 0 the block is at its furthest left negative position, x0 equals negative a, and its velocity would have to be 0 there when it's at the turning point, we can plug in x of t, which is a cosine omega t plus phi. We plug in t equals 0, and we see x of 0 is a cosine phi, but we know from our initial conditions x at 0 is negative a. So we want cosine phi to give us negative 1. Our only solution here is 180 degrees. We don't have to look at the velocity in this case. If we had used sine instead, we plug in t equals 0. Again, we know that x at 0 has to be negative a. And if it's a sine phi, the only answer is negative 270 degrees.